Hello everyone and welcome to this theory recording on complex numbers. So the importance of complex numbers in this particular chapter is that it will allow us to be able to deal with the different types of values that we would need when working with all elements that we will be using. So that is the capacitor, the inductor, and the resistor. Right, so what does the complex number scale look like and how does it come to be? What we are familiar with at this point is the real number line, which takes into account your whole numbers, your natural numbers, your rational and your irrational numbers, right? But what happens when we have a value or a sum, for example, that says the root of -9. So historically we know that that would give us a value that we would say is non-real, right? Or if you apply imaginary numbers, then what we do is we say the negative becomes a j squared times 9, and this is going to give you now plus or minus j3, and this introduces us to the imaginary number line. So we know that the imaginary number line will have a j at the as a prefix to the number itself, whereas the real number line has the actual number, right? And this now allows us to deal with both real as well as non-real numbers. So I could have a value that is x is equals to 2 plus j3, and that basically tells me that it's going to be 1, 2 in the real, and then 1, 2, 3 in the imaginary. So this will be the value of 2 plus j3. And this is now how we go about dealing with complex numbers. Polar and rectangular form, these are two forms that one needs to be able to shift easily between. Alright, so polar form is more your vector form, which gives you the real and the imaginary component. So 3 plus j4, that will be 1, 2, 3 real, and then 1, 2, 3, 4 imaginary. So 3 plus j4 will then sit at that point. And this is your rectangular form. We also have polar form, and polar form is typically your magnitude and your phase. So it will be V1 angle theta, for example. And how will we get this? We can get this by using trigonometric functions to get the hypotenuse of this. We can also use Pythagoras. So we can say the hypotenuse, which will be r, is going to be the root of 3 squared plus 4 squared, which then gives you 5. So you'll have a magnitude there which will be 5, and you'd have to then calculate the angle. So that will be the angle of 3 squared plus 4 squared. So 3 plus 4, and that gives you an angle of 53.13 degrees. So polar form, x is going to give us 5 angle 53.13 degrees. Let's take a look at the different domains that we will be working with. So the first domain that we're familiar with is the time domain expression. So that's the expression where we're going to be saying Vt is going to give us Vm cos of omega t plus theta v. So that's the time domain expression. Then we have phasor form, or the frequency domain expression, where we can say then the voltage, let's call it phasor, is then equal to the magnitude Vm angle theta V. So that's your polar form. It's also known as the frequency domain or phasor form. We also have exponential form, polar form, and rectangular form. So let's work with the signal x equal 3 plus j4. So we know now that this is in rectangular form. And how do we get this to polar form? So x in rectangular form gives us that value. X in polar form we know is going to give us 5 angle 53,13. What about x in exponential form? In exponential form, what will happen is that you would have a constant. So let's call the constant a, e to the j theta. So xe will actually equal to the constant, which is basically the magnitude 5 e to the j, and the angle will be 53,13 degrees. So you should be able to see how to move between polar form and exponential form, and how to move between rectangular form and polar form, and also how to move between the time domain expression and the frequency domain expression, which is your polar form. Thank you for watching this video and enjoy the course.